A lot of research goes into the animatronics that we create at Strange-Twig Theatre Company. We like to make sure that there's a lot of veritas, a lot of truth to what we make. The renovation of Monty, our Clockwork owl, has been a project that we've been planning to get round to for some time, and we were very glad that we finally had enough space in our schedule to bring him up to the quality that we know we expect of ourselves and other people expect of us. So right now what I'm doing is fitting the bearings for the owl's second wing. First wing is already completed, and I've nicely inset the lock nuts there, and the bearings making a nice fluid motion. I've pre-cut using a rotary tool an 11mm hole with a 6mm hole through the bottom, 11mm hole at 4mm deep, and then the remainder at 6mm, and that's so that the lock nut can sit neatly against the base of the bearing, and then on top of the bearing will go a washer. I'll use a drop of super glue around the edge of the bearing just to hold the bearing in place. Obviously this wood's got a bit beaten up during the process of making these pieces. They're quite intricate and quite small, a little bit fiddly. This is the perfect shape they need to be in order to fit into each other and create the correct motion for the wing. So what's going to happen after the owl is completed is it's going to be completely taken apart again, and all of the pieces are going to be individually wood stained to make them look uniform. So you can see here what's going on with Monty after this recent period of construction. We've got the bearings in both sides of the wings, and also the universal joints leading to each wing and the pivot point in the middle. You'll notice that those armatures are asymmetrical. There's also an asymmetrical armature in the tail. The only symmetrical armature is actually the one that makes the owl's head rotate. And we find that with a lot of our animatronics, actually asymmetrical armatures tend to be the best for symmetrical movements when you only have a single actuator, that's a servo or a motor of some variety, something that creates movement, performing that action for the animatronic. I'm going to test the motors now and the servos and just check that everything is working okay, all of the articulations. Seems to be a little bit of strain on the wings there. So the servo that I had set up for Monty's wings wasn't powerful enough, so what I'm going to do is I'm going to cut some extra space inside Monty's body, and I'm going to fit a much more powerful motor in there, and I'm going to have to build an H-bridge out of relays and work out a new place to put all of his batteries, because none of it's going to fit anymore. But that's okay. That's part of the iterative process of creating an animatronic when you have unknown mechanisms that you're trying for the first time. So that's what I'm going to do now. Safety first. I'm using loud power tools, very loud power tools. I got some earplugs, got my face mask. Here we go. One of the things that I've mentioned is an H-bridge, and I'm often asked how we create the electronics that go into our electronic-based props. So I thought I'd take the opportunity to show you what an H-bridge actually is. Now, an H-bridge is an electronic device. This is one that I've just whipped up right here. And it allows a motor to have the polarity reversed so that via a signal from an Arduino through one of these two cables, I'll explain how this works in a minute, the shaft of the motor will either turn clockwise or anti-clockwise. A motor turns one particular direction when power is given to one point and the other point is grounded, and that reverses when the power and ground are reversed on the motor. And this little device here, or things like this, allow us to do that with the aid of a microcontroller or other means. I'm using an Arduino. It's a very common open source microcontroller or miniature computer. So what I've done here is I've used two relays to create my H-bridge. Here's a circuit diagram, basic circuit diagram that I drew years ago now from a little bit of thought and a little bit of research. I've used relays in this situation. You can use transistors. I've chosen not to use transistors. They get quite hot, and Monty's made of wood, so I don't want to cause any problems with heat inside an enclosed wooden shell. Relays don't get hot. These relays can also cope with up to 10 amps going through them, and that's more than enough ampage for what I want, which is to power the motor that moves Monty's wings. So what I've done here is the common point on each relay goes to either point on the motor. Now, in this instance, to demonstrate, I've attached it to a multimeter so you can see the change in polarity as the voltage changes direction, which would cause a change in direction of the motor. The central point here is two connected pins, two connected legs of the electromagnetic coil inside the relay, and they're connected together and they're sent to ground on the microcontroller so that a signal can be received. The remaining two legs of the coil, one per relay, will receive the signal from our microcontroller in the form of 5 volts at about 40 milliamps. On the other end of the relays, the normally connected and normally open points have been connected together. So that's the normally connected point of this relay connected to the normally connected point of the other relay, and the normally open connected to the other normally open. The normally connected points that have been connected together are sent to ground of the power supply that you're powering your motor from. This is so that when no signal is being received, no power is being drawn, the circuit is completely shut off, and you can see the multimeter reads 0. However, when the coil is activated and the switch flicks on either or of the relays, power will go one way or the other around the circuit. And if you can see the circuit diagram here, you can see that power comes in via the 5 volts here, or however many volts it is, and travels through the circuit and back to ground, and the motor here is fired. If that were reversed, then power would travel the other way around the circuit, and the direction of the motor would be reversed. So it's a fairly simple circuit. I hope I've explained that okay. And what I'm going to do now is show you what happens when we connect one of our signal leads to 5 volts. Now this is just coming from the Arduino. You could send a signal via a signal pin. That's how I'm intending to do it. Never ever have both signal pins connected at the same time, because you'll create a short circuit and you'll cause damage to your electronics. So if I connect this signal pin here, the relay fires, and we've got reverse polarity of about 4.9 volts. Negative polarity, rather, according to the multimeter. And if I connect the other, and the other relay fires up, we've got positive polarity of 4.9 volts. So, with regards to Monty, what that means is that the motor, being powered by the batteries in the animatronic, can be sent in either polarity to the motor. When it gets sent one way, the wings will open. When it gets sent the other way, the wings will close. Everything's looking really good on Monty now. I've managed to pack in all of the electronics pretty much. I'm still waiting for a Bluetooth module to arrive, but I'll install that once it does. Managed to get the H-bridge in under the Arduino Pro Mini there, which is really good news, and there was just about enough space for all of the battery packs. I've even managed to get both of the limit switches in there as monitoring devices for the wing opening mechanism, and they're functioning really nicely. So I'm very happy with things so far, and Monty's upgrades have gone really, really well. Monty's now pretty much finished, so that just leaves us a little bit of time to show you how he's turned out.